कधी सुरू करू बघ. अजून 2 मिनिटं थांबू का?
नाही सर, स्टार्ट केलं तरी चालेल.
ओके. शेअर करूया. Good afternoon. I'm going to begin my second lecture today. So I will continue with the theory of black holes, which I started yesterday. And following that, I'll talk about how stellar mass black holes are formed, and then leave the rest for tomorrow. So to recapitulate what we did yesterday, we were looking at the motion of a particle, a massive particle, in the gravitational field of a Schwarzschild black hole. So there we found that the best way to study the problem is to define what is called an effective potential. So you've got the effective potential here, where the first term is the Newtonian gravitational attraction per unit mass. The second term is the centrifugal force. And the third term is the general relativistic contribution. So if we did not have general relativity, we are doing our calculations only within the framework of Newton's theory, then we would have this particular curve here. So this is the minus 1 upon r part, and this is the 1 upon r square part. So the centrifugal part is the repulsion and the gravitational part is attraction. So if we had a particle coming in from infinity with a certain amount of positive energy, then it would come down the sun, it would begin to go around the sun. At some point, it would come to the closest distance of the sun, and then it would shoot away, just like a comet. So in this diagram, we apparently find that the particle comes, has a turning point, and then goes back. But in reality, in space, if you are looking at this orbit from the top of the sun, then you would see the particle coming in from infinity, swinging around the sun and going. On the other hand, if you have got a particle of negative energy, then it would be in a bound state. So in the Newtonian case, this state would represent an ellipse. So it is like a planet which is going around the sun, where the effects of all other sources are neglected. Okay, so then you will get an ellipse like this. So this would be an elliptical figure. But as you go closer, and if you have more energy, at some point the orbit would be located here at the bottom of the potential. So now when we come to the where it would be a circle. Now when we come to the general relativistic part, so you see that the centrifugal repulsion takes you up and up and up, except that because the black hole, when you get sufficiently close, the black hole attraction dominates the centrifugal force, and then the potential again turns over and comes down. So we have seen in Newtonian case, because you understand that this goes to infinity. So even if you have the smallest amount of angular momentum, the particle will always go back to infinity. Not so in the general relativistic case. Because here, for example, you may have solid angular momentum, but as you go up here, meaning that you have more and more energy, then you could cross the barrier and crash into the black hole. So now, just like you have the closed orbits here, you also have closed orbits in the potential, in the general relativistic potential. But there, the orbit will have a slightly more complicated shape than an ellipse. And that is because of the 1 upon r cube term. The net result is that the ellipse seems to be precessing with time. Okay, meaning that the point at which you've got the minimum in the ellipse keeps going around the sun. And that is responsible for the precession of the perihelion of Mercury. Right, so here are a couple of orbits shown. So this corresponds to a particle which has come from infinity, goes around the sun, and then goes to infinity. Where this orbit here, which you see, that corresponds to uh, a particle which comes in from infinity, okay, and then no, I'm sorry, it is this particle that you're talking about, which is the line of zero. This particle comes in from infinity. It has angular momentum, therefore its orbit is curved. But then, as it crosses the barrier, and just goes, it disappears into the black hole. So here is a other orbit. So you've got here a particle sitting at the bottom of the potential well, and that corresponds to this particular orbit, a circular orbit. Whereas if you've got a particle sitting at the top of the potential well, then you'll again get a circle because r is equal to constant. The circle has much smaller radius. But what is the difference between these two orbits? This orbit is stable. Okay, meaning that if I give the particle slight energy, then a slight kick, then the orbit will, instead of being a pure circle, will become slightly elliptical. So you can go on making it more and more elliptical by giving it more and more energy. The stability means that it can remain at the bottom of it remains bound. Where the particle which is sitting here, so that is unstable. Meaning that if you give it a kick here in this direction, it will go up to infinity. Whereas if you give it a kick in the other direction, then it will fall into the black hole. So now let's see. I'm going to make a very important point here from the point of view of uh, observational properties of rotating and non-rotating black holes. And the property is the following. Now here again, we have got a general relativistic. These are in general relativistic orbits, the Schwarzschild orbits. But now instead of showing you just one, the dotted one is the Newtonian one for reference. And these here, they correspond to different values of the angular momentum. So you see that you've got the angular momentum here, and the angular momentum in these units, where c is equal to 1 and g is equal to 1. Angular momentum and mass have the same units, and so they are basically dimensionless. And what you do is that you get here, this is L by m is equal to 4.5 L by 2 root 3, etc. So what happens here, you see that as the angular momentum increases, you know that when the angular momentum is zero, it can reach, it just goes a straight line and falls into the black hole, whether it is a Newtonian case or a relativistic case. But when you've got a finite angular momentum, then you get these potential wells. You see that the lower the angular momentum, the closer is the minimum moving to the black hole. It's a very important point because the minimum is going closer to the black hole. So where are the minima actually? You'll obtain that by saying dV by dr is equal to 0. But you remember that you've got a V effective potential, V effective. So now you just put d by dr, V effective is equal to 0. Because that is how you find the maxima and minima in a function. And when you do that, you will you find that you'll get two solutions. Why do you get two solutions for the derivative is equal to 0? That is because in the general case, we have one minimum and one maximum. So for a given angular momentum, the minimum, these are interchanged. The maximum occurs at 1 plus this particular term here. And the minimum occurs, instead of max, just read minimum here. Minimum occurs at 1 minus this. So what does it tell you? Is that the minimum is closer, to R, the lower the angular momentum, because I'm go on lowering this one. Now you'll see that for a particular value of the angular momentum, that is L is equal to m by L square is equal to 1 upon 12. That is L is equal to 2 root 3. The m. When that happens, this term is equal to 1, therefore this term is 0, and therefore you will get R minimum is equal to R maximum. They're just 1. And this is the corresponding curve here. And what is the significance of this curve? And this is a curve. This is the value of the angular momentum that a particle can carry, for which you have got what is called a marginally stable orbit. Do you get that? Because when you are here, there is certain stability, certain stability. So here, the stability is very marginal, meaning that R min and R max are coincident. So now, if you lower the angular momentum further, then there will be no minimum, not a maximum, which would mean that you cannot have closed orbits. Right? So why is this so important? Why am I stressing this so much? Now, what happens is that when you, if matter starts falling into a black hole, because it carries an angular momentum, it builds an accretion disk around the black hole. Once you've got an accretion disk, you take the matter in the accretion disk. That matter, at any given orbit, at any given point of the accretion disk, at any distance r, it will be moving with a certain velocity. The orbit inside is with a higher velocity because as you go closer to the gravitating center, you must have higher velocity, and the orbit outside is lower velocity. So because of that, there's a viscous drag between the particles, as a result of which the particles which are moving faster, so they give energy to the particles which are moving slower. And in the process, the particles which are moving faster will move closer to the black hole. So you see that imagine that the particles were here and they had particles were here. Then as you will keep the angular momentum, if you keep the angular momentum constant, if you reduce the angular momentum also, then they will start moving closer and closer. And at a certain point, when you have removed both energy and angular momentum, at a certain point, what will happen is that they will reach the marginally stable orbit. If you remove further angular momentum because of the viscous drag, then the particles will just plunge into the black hole. So which means that what is the innermost, the closest radius that an accretion disk can have to the black hole, that is equal to this particular radius when L is equal to root of M3. And that radius, I can't see the thing here because of. So you'll see that particular radius, which is known as the innermost stable circular orbit, that is equal to 6 gm by c square, which is 3 times the Schwarzschild radius. So please remember this, because I'm going to again talk about it when I go to rotating black holes. Is that when you've got a Schwarzschild black hole, then the innermost stable orbit which is possible, it has 3 times the Schwarzschild radius. So if the sun were a black hole, then the innermost stable orbit around it would be 9 kilometers in radius. And so here you can see the innermost stable orbit. Right. So now I'll very quickly mention it. I'll not be able to talk about it at all. Is what happens if you consider the orbit of a photon. So you see that when you have, we saw that there was a potential well possible for massive particles. But when you take massless particles, and these correspond to what are known as null geodesics. Okay, because massless particles always move with the speed of light. So if neutrinos were massless, they would be moving at the speed of light. Photons move by definition at the speed of light. Right? So when you have particles like that, then it turns out that the potential depends only on what is called the impact parameter, which is another name for angular momentum, you can say. And there's just a maximum, and there is no minimum. Right? So what are the possible orbits? So if you have got a photon, a beam of light which will shine it towards the black hole, not exactly towards the center, but away from it, so that the photons have angular momentum relating to the black hole. Okay, then just like a particle, they'll come up to some point and go back. Meaning what happens in physical space, this is energy space. What happens in physical space is that the photon comes from a distance, is attracted by the sun just like a particle, it bends its trajectory and goes away like this. Whereas if the photon has greater energy, then it is at a greater height than the barrier, in which case the photon comes in, goes round and round and round, and then just falls into the black hole. But it can really fall into a black hole after many different orbits. So now just imagine that I reverse the direction of time because the theory is time invariant. So a photon which is kicked out, thrown out of here, okay, would go round and round and round and round and then escape the black hole. But the most interesting is a photon which is sitting at this stable point. And because it is at a constant, it remains at a constant R, meaning it just goes round and round and round at this radius. And what is this radius? Now, this radius is 1.5 times the Schwarzschild radius, the point where you get the maximum. It's a very interesting. So, so you see that you've got a singularity here. This is the Schwarzschild radius. So this is not to scale. Because this is a Schwarzschild radius. This is not to scale. 1.5 times the Schwarzschild radius. And then photons there, each photon goes in a circle, but you can have photons in different directions so that you can actually get a photon sphere. And this actually happens in reality also, and simply because that is how you got the first picture of the black hole. Right? But these orbits are all very unstable. A photon can just drift away from the orbit, but other photon will be placed. These extremely interesting concepts. All right, so now I leave Schwarzschild black holes behind, and then I come to a rotating black hole. I'll be very, very brief here with rotating black hole and point out certain dramatic differences between this and the Schwarzschild black hole. So first of all, first, so this is Roy Kerr, and he's from New Zealand, and he's the one who discovered the solution of a rotating black hole. So you see that in 1915, Einstein gave the general theory of relativity. In 1916, Schwarzschild gave the solution corresponding to a point mass. And it was 48 years after that, in 1963, that Roy Kerr gave a solution corresponding to a rotating black hole. So am I saying that there was no exact solution of general relativity found between 1916 and 1963? That is not true. And for example, there are any number of very important cosmological solutions. There is the Einstein DC to space, and then the Robertson-Walker metric and the Feynman inverses and so forth. There are any number of cosmological solutions. Also, there's a whole industry which works on finding exact solutions of Einstein's equations. So there are hundreds of solutions, they're all been classified, and there's a great deal of theoretical work which can be done with them. But here we are really talking about astrophysically important solutions. So it took 48 years after Schwarzschild's solution for Roy Kerr to find a solution corresponding to a black hole, a rotating black hole. So I already told you at the beginning of my lectures that black holes can have mass, spin, and charge, and nothing else. Okay, so charge we are discounting because matter is neutral. And when you have a charge, for example, the black holes can have very, very interesting structure. If it is a Schwarzschild black hole, then with a charge, then it is called Reissner-Nordstrom black hole solution. Whereas if it is a rotating black hole, this is the Kerr metric, Kerr solution. And if you have got a rotating black hole with charge, it is called the Kerr-Newman solution. But I'm only going to stick to the Kerr solution. Now, I will just show you the metric corresponding to the Kerr solution. I'm afraid I cannot explain it to you. So we had the flat space metric of special relativity, and then we had the rather simple metric of Schwarzschild solution, corresponding spherical symmetric metric, and this is cylindrical symmetric because you see that you've got a particle which is rotating. So there is axial symmetry there. And so you see here, it's much more complicated than the Schwarzschild metric. And what is important is that in the Schwarzschild metric, you have only one parameter, which is the mass. Now you have got the spin. So you have got an angular momentum. And what you do is that you use the parameter A, which is called spin parameter, which is equal to the angular momentum per unit mass. And these quantities are defined here for continuous. They are not fundamental quantities. But what happens is that you can, so you've got angular momentum per unit mass. And what I can say is that there is, just like in the Schwarzschild case, there is a singularity at r is equal to 0, which is a real space-time singularity. So here also you have got a real singularity at rho is equal to 0. Okay, but you see that it's very, very interesting there. Because in the Schwarzschild case, you have got the singularity at r is equal to 0. The other coordinates are not specified, they're impertinent. So what happens is that the singularity is what is called a point singularity. But in this particular case, you see that rho is equal to 0. For rho to be 0, you need two conditions to be satisfied. One, r is equal to 0, and the other, theta is equal to pi by 2. You please see that these are independent conditions. So if I just have theta is equal to pi by 2, it will be a finite value of r. If I have just r is equal to 0, then rho will not be 0. Both have to be 0. So which means that the two conditions, r is equal to 0 and theta is equal to pi by 2. So these two conditions tell you that therefore it is what is called a ring singularity. So if you approach r is equal to 0 or any other value of the polar coordinate theta, then you will not get a singularity. Only in the equatorial plane, where theta is equal to pi by 2, that is where you have got the singularity only in the plane. And that is therefore it is called a ring singularity. And there's another amazing thing. Now when delta vanishes, so imagine A is equal to 0. Okay? So then what would it mean by delta vanishing? That R, take R outside the bracket. So you get 1 minus 2m by R is equal to 0. And you'll remember that is the definition of the event horizon in the Schwarzschild case. So when I got A is not equal to 0, then you can prove that delta is equal to 0 is again the condition for obtaining an event horizon. So therefore, but then when delta is equal to 0, please see that this is a quadratic equation. And therefore delta is equal to 0 gives you two event horizons. One is r plus, which is equal to m plus square root of m square minus a square, and the other r minus, which is m minus square root of m square minus a square. Right? So, so then there is also another condition. So you have got two horizons, and also another condition. And that condition is that A must be less than M. You see that? A is less than M. And because if A becomes greater than M, okay, then you will have, R will become imaginary, which you really don't want. So, therefore, a curved solution with an event horizon has a maximum value of the angular momentum. And that happens when A is equal to 1. When there A by M, I'm sorry, A by M, A is equal to 1, which means M is equal to G. M is equal to G. So you see, then what happens when A is actually smaller than? Because I have got A greater than 1, M. I have not put that condition here. Right? I have not put this in the metric. So which means that solutions with A greater than M are also possible. And there, solutions with A greater than M are possible. A greater than 1 are possible. So there what happens is that you have, but then you get what is known as a naked singularity. Okay, that is because there is no event horizon, which most people think is unphysical. But there's a lot of work going on there. So what is the net result? Is that we have got, you see that this is the Schwarzschild, this is a curved black hole, and you have got the ring singularity here, and you have got an event horizon outside, which is the event horizon which corresponds to our Schwarzschild surface. And so anything which enters the event horizon cannot go out again. It's a one-way membrane. And then you have got an inner horizon. Now the inner horizon simply can never be seen from the outside because we cannot see anything from inside the event horizon. So therefore, it is of more practical consideration. But on the other hand, theoretically, it is very interesting because the nature of space-time changes from the region between the two horizons to the region inside the inner horizon. I'm not going to be able to go into that at all today because that will take us too far afield. Then you have got another surface which is known as the static limit. And I can only mention it. What happens is that the spin of the black hole, is a very powerful, just like the gravity of the black hole is very powerful. The spin of the black hole also can get very powerful. And if any particle enters the static limit, you can enter the static limit and you can leave the static limit. It's not event horizon. When you enter the static limit, then you are compulsorily dragged round and round and round. You cannot, if you look at the distant stars, you find that you're going round as if you're on a merry-go-round. Okay, so so you are compulsorily dragged around in what are these rotating frames. Okay, so that is called, this point is called the ergosphere. And it was shown by Roger Penrose many years ago that you can extract the spin energy of the black hole by carrying out certain uh, rather strange maneuvers here in the ergosphere. And then there have been many speculations on that with a big magnetic field. And Professor Naresh Dadit of IUCAA and his students many years ago also showed, gave another process which is analogous to the Penrose process. Right, so then now two important matters here. Here is a plot. So you remember that in the Schwarzschild case, we had an orbit which has got the innermost circular orbit, innermost stable circular orbit, ISCO. And at what point did it occur? And it occurred at r is equal to, sorry, at r is equal to 3rs. Okay, so you see here, now what happens is that if you have a rotating black hole, then you've got different values of A by M. And then you could, what you could do is find the ISCO corresponding to each value of A. And this is from Hartle's book, and this is a plot of R ISCO by M against the A value, A by M. And what you see here, so this is co-rotating orbit, meaning that this is for a particle which is going around the spinning black hole in the same direction as the spin. And this is for counter-rotating orbits, meaning for when the orbit is in the direction opposite to the spin of the black hole. Okay, so for a co-rotating orbit, you will find that when A is equal to 0, you are at the Schwarzschild solution. R ISCO is M, which means that it is so it is 3M, is 6. And so that is, this is just 6M, which is equal to 3 times the Schwarzschild radius. Right? But as you go on increasing A towards its maximal value, I told you that A by M can maximally be 1. Okay, so so then when you come here, you will find that the ISCO, the radius of the ISCO, I written it down somewhere here, the radius of the ISCO is equal to 1.25 times the Schwarzschild, times the event horizon radius. So you will see that in the case of a rotating black hole, you can get much closer to the black hole and still have a rotating, stable rotating orbit. Now, similarly, here is another thing which shows what is the amount of energy you can extract from the particle. So, because let us say that the particle is orbiting a black hole at a great distance, then I can remove energy from it, in which case it will go closer and closer and closer. And how close can it get and still be rotating? It will be at the ISCO. So, so here again, I have plotted Hartle. I have not plotted it. Hartle has plotted it. So I got A by M here, and then you got 1 minus E. 1 minus E is the binding energy because it starts with an energy. They've got energy here. At infinity, they've got energy of 1. So 1 minus E becomes the binding energy. This is the amount of energy you would have to give the particle to remove it to infinity. Or you can say the amount of energy which has been released in the particle to the ISCO. And so how much is it? So you will find that when A is 0, again we are at the Schwarzschild surface, when you are at the Schwarzschild surface, and A is equal to 0, it is only 0.057. So about 6% of the energy of the particle can be extracted by sending a particle to an orbit with the ISCO. But if you have got a maximally rotating black hole, extreme curve black hole, there is A by M is equal to 1. So in that case, you'll see that you can get as much as 42% of the energy. But you can never ever reach A is equal to M. So why is that? That is because as you go on increasing the value of A, it becomes closer and closer to M in dimensional units. Then the black hole will be rotating faster and faster. So just imagine, let's suppose that you are trying to throw something from space onto the Earth. You know, you've got all these meteors and things that are coming and falling onto the Earth. But let us suppose that the Earth starts spinning faster and faster and faster. So as these things come, they'll be dragged by the Earth's speed and they'll go around it. But at a certain speed of the Earth, then the centrifugal force will be so much that the particle trying to come in is thrown out again. So this is exactly that. Because as A approaches M, then you require infinite energy to reach the response. But then for A smaller, for A is equal to 0.998, because this is dropping very rapidly. So for A is equal to 0.998, then the efficiency is 30%. So you say, what can you compare this efficiency with? You compare it with the efficiency of nuclear fusion processes. Because when you've got nuclear fusion, so you'll see there that you're bringing together 4 hydrogen nuclei, which are just protons, and out of that forming helium and releasing energy in the process. And what is the amount of energy which is released? Is just 0.8% max. Okay, the fusion of helium, of hydrogen to helium. So that compared to that, these processes will be far, far, far more efficient. So if you have, so because this is 42%, that's 0.8%. So, but we still don't know how to remove energy from black holes to generate power for the Earth, for example. All right. So I have finished with the theory of black holes in a matter of speaking. And I'll take a pause here for a few minutes. And so if somebody has questions, I can try to answer them. There was one here. Sen Gupta. You have a question?
Hello, sir. Am I audible?
Yeah, I can hear you.
Sir, my question was from the first part of the talk when you were explaining the accretion part. As the matter falls inside the black hole, since it has an angular momentum, it results in the formation of the accretion disk. So my question is, what dominates or what measures the orbit of the accretion disk? Like the way it will be formed, or in which pattern, or in which direction the accretion disk is going to be formed? Is there anything that is measuring that part? Because every time the matter falls in, it forms a disk. Why it's not a sphere?
No, it is not a sphere because it carries angular momentum. See, just imagine matter coming in from outside. All matter has angular momentum. They really, anything which is coming, let's say that something which is falling onto the sun, falling onto the earth, falling onto the moon, you will always find that it has zero angular momentum if and only if the trajectory of the particle is directly intersecting the center of the earth. If it is not, then it will always have angular momentum. Then if it has got angular momentum, you see that it is coming in a plane, right? Because angular momentum is conserved, and therefore the motion of a given particle will always be in a plane, and that is how you get Kepler's laws and Newton's theory and so on. Now, if you have got a spherically symmetric cloud of particles which are falling on the black hole, then the accretion will be spherical symmetric. But that never ever happens in reality. It happens very rarely, actually, not never ever. And so mostly because the matter coming in from a star has got angular momentum. So I will show you an example of that second part of my talk. And then you will form an accretion disk in a plane which preserves the axis of rotation of the disk is determined by the angular momentum which is coming.
Okay.
Any other question? Yeah. Eshicha Chan.
Hello, sir. Ishika.
Eshika, okay. Sorry, tell me.
No, sir. What do you mean by the efficient energy of the black hole? Like, I couldn't get it.
No, it's not. You see, what happens is that let's say that you've got a particle which is at infinity. Okay? So, and the energy at infinity will be m upon square root of 1 minus v square by c square. right? So now suppose V is equal to 0, the particle is left, it has got only its rest mass, there's no other energy. As it starts falling in, you see that if the energy is conserved, then you know that it will form a certain kind of orbit. But if I remove energy from the orbit, I remove it because of, for example, viscous drag, then as the orbit has more and more negative energy, okay, then it will move closer and closer to the black hole. Okay, this is black. There's nothing black. It's not important that it's a black hole. It's just a spherically. You just have gravitational attraction. That's. But now the more energy. So the closer the particle moves to the center, the more negative the energy of the particle will be, which means that much energy has been removed. So what is the closest that it can have a circular orbit in? It is the RISCO, ISCO, right? It is the innermost stable circular orbit. So for a curved black hole, I showed you that it will be 1.25 times the Schwarzschild radius, right? So therefore, now you can calculate what is the energy there, and then you will find that 1 minus E upon E is equal to 42, is 0.42, which means that 42% of the rest mass energy of that particle has been extracted from the body.
Okay, sir. So
Yeah.
it's a general one.
Yeah. So, Shriya.
Good afternoon.
Just one. Yes, please.
Good afternoon, sir. So my question is from the slide of the innermost stable orbit for black holes, where we calculated the minimum R for the black hole, where after which the particle falls into the black hole. So there we also calculated for the formula for R max. So what is this R max signify?
So R max is you saw that the potential had a minimum and a maximum. So R max is where R max is the outermost one. Okay, where the maximum in the potential occurs, and R minimum is where the minimum in the potential occurs. Okay, so sorry, let me go back and I think I've made a mistake at this point. Just one moment, please. Okay, so for, do you see my screen?
Yes, sir.
Okay, so you see, R min is where the minimum of the potential occurs. For this one, it is here. Okay, and so this is outside because it is 1 plus. It is 1 plus this term, and R min is the R max is the point where the maximum in the potential occurs. Do you see that? And then for the marginally stable orbit, this is equal to 0. So R min is equal to R max. So both this point and this point are combined together at this point. See that?
Yes.
Okay, great. Any other question? Ayush Garg? Ayush?
Hello, sir. Am I audible?
Yes.
Sir, I have a question from the black holes accreditation disk. We have seen that there are two types of it. In the first one, the center of the black hole is bigger and the accreditation disk is of a lesser thickness. And there is another one in which a black hole is a very small point-like structure, and the accreditation disk is
it moves closer. It moves closer. If you have got a neutron star, what I suggest is that you please write me this question and then I'll send you the answer. Okay? In the thing. Yeah. All right. Anjali, last question, Anjali.
Yes, sir. Hello. My question is to what kind of objects apart from black hole we can apply this innermost stable orbit concept? Is it possible to apply for neutron star?
No. This is specifically in order to have these stable orbits, such innermost stable orbits, etc. You have to go very, very close to r is equal to 0. That is only possible in the case of black holes. So let us suppose that you have something like a neutron star instead of a black hole. A neutron star is also an extremely dense object. It has got a radius of only 10 kilometers. And then when you can, but then much smaller compared to the radius of a star like the sun. So you can have very powerful gravitational fields there. But as the matter spirals in, there is no innermost stable orbit. So finally, the matter will actually hit the surface of the neutron star, and that is going to be very important in the interpretation of X-ray binaries. I'll bring up this point later in my talk.
Okay, sir. Thank you, sir.
Okay, all right then. So we'll go back to the lecture. So we're done with that. And so what I'm now going to talk about today is the rest of my talk is the formation of stellar mass black holes. How do you form these black holes? What is possible? So now these stellar mass black holes, meaning black holes in the with mass in the range of 1 to 100 solar masses, are typically the products of stellar evolution. So let us see what is the meaning of that. So here is the star, which is actually the sun, and the sun only all stars of the mass of the sun would be like this. So what is the sun? If you take a cross section of it, then you will find that you've got the core, there's the central region of the sun, which is at a temperature of about 15 million Kelvin. Okay, inside. And then as you go outwards, it gets cooler and cooler and cooler, and then you come to the surface, because you see that the sun has largely yellow color when you look at it, and that tells you that the temperature is about 6,000 Kelvin. So because it is so hot in the center, you can have nuclear fusion going on. And as you know now, and what you don't know will be taught to you during this course, is that because the temperature is so high, the hydrogen which is present there is getting converted to helium. And in the process, energy is released. So that energy keeps going out. And that is how we can exist here on the earth, because of the energy which is coming to us from the interior of the sun. Now the sun has got a mass of 2 into 10 to the 33 grams. And about 0.8% of that mass can be converted to energy. And so even though the sun is so large, so massive, it is also emitting energy at the rate of 4 into 10 to the 33 Earths per second. So eventually, in about 10 billion years, the 9 billion years or so, the hydrogen will be completely exhausted. When the hydrogen is exhausted, the energy generation stops. So the star becomes slightly cooler inside, and the matter inside will start collapsing. And at the same time, because matter collapses, gravitational energy is released, and the outer part is heated, and it starts expanding, and it becomes a red giant. But the inner part, which is collapsing, because you see gravitational energy is being released, and then, so therefore, it starts getting hotter and hotter. And eventually, it becomes so hot that the pressure can again balance the force of gravity. And when that happens, it stops, and the temperature will be so much higher, more than 30 million Kelvin. And at that point, the fusion of helium begins. So when helium is exhausted, you'll again have a similar cycle. And then in principle, you could go you could come hydrogen, helium, carbon, nitrogen, oxygen, and so on. And you can go up to iron. You cannot go up to iron because the binding energy there is such that in order to carry on fuse iron to heavier nuclei, you require an input of energy rather than output of energy. Now, the sun is never ever going to make iron in its core. That is because the maximum temperature that you can have of the core is proportional to the mass of the star. And for the mass of the sun, the temperature will never become high enough to go beyond carbon, nitrogen, and oxygen. So then when that happens, the sun collapses and it forms the carbon, nitrogen, oxygen white dwarf. And the outer layers are completely thrown out. For a more massive star, uh, you can form, you have a neutron star which can be formed at the center, and the outer layers are thrown out in the form of a supernova. But when the mass is really high, meaning let's say mass is more than about the mass of the starting star is more than about 25 solar masses, then even a neutron star is not, you cannot form a stable neutron star, and then what you get is a black hole. So you see that here there's a picture of the hydrogen burning in the core, and here you have got the core, the helium is burning in the core, then there's a hydrogen shell, and then there's the photosphere, and here you have got, you see, iron, this is a star which has got the whole hop. So iron, and then you, as you go outwards, you get progressively the less heavier nuclei. Okay, and then each time the center collapses, what happens is that you see that you must have heard about the main sequence of stars, and then the sun is sitting somewhere here, but this particular star is sitting here, and so you see that as each epoch of conversion goes through, the star first expands, cools, and expands, and it goes like this to a gulliver. Eventually, it bursts into a supernova. Right, so when it goes into supernova, the central part is collapsing. Now, I'm going through this very fast because that is not my intention to explain to you these matters. They will be done separately by people who are considering stellar evolution. But what I'm interested in is the end product of the gravitational collapse. Okay, so you'll see here that what are the masses? Everything depends upon the mass of the star. You see, a star, a black hole has got only the mass, right? Its property. A star, the properties of a star are defined mainly by the mass of the black hole, mass of the object, plus is also defined by its chemical composition. So, so you see that when you've got a mass, which is if the mass of the aggregate is less than 0.01 solar masses, it can never form a star. Why cannot it form a star? Because the temperature at the center is not enough ever for nuclear fission to be set off. And in fact, it forms what is known as a planet, like a Jupiter would be something like this. Then, if you got in the next range, you form what is known as the brown dwarf. And then when you come to higher than about 0.1 solar masses, I mentioned this to you yesterday, then you'll form a star. The star will burn hydrogen to helium. Eventually, the hydrogen will be exhausted. The temperature is not enough for the next cycle of burning, so it collapses to form a white dwarf. And the outward part is thrown out in a nebula. And you see, right up to 12 solar masses or so, these limits are not hard limits. They depend on many assumptions. So you'll see you get a helium white dwarf, a carbon oxygen white dwarf, and an oxygen nitrogen magnesium white dwarf. Whereas if the starting mass is between 12 and 40 solar masses, then the object will be formed with a neutron star. And for M greater than 40 solar masses, you get a black hole. So then you see, therefore, you can say that black holes which are related to stars, okay, a black hole with mass comparable to the mass of stars would be formed from during the evolution of stars. So they're pretty well worked out. Okay. So you see, now you form a black hole, and this is just a cartoon. Don't take it very seriously. And it is a depiction of all the matter pouring into the singularity and during the collapse. And what you will get is that you will get an object which is either spinning or not spinning. It's more likely to be spinning than not spinning. And then there'll be, at the center, there'll be a physical and mathematical singularity. And we have seen how to live with that singularity. Okay, so let us suppose the black hole is formed. Then how will you detect the black hole? As I told you, very difficult to detect an isolated black hole. And that is because you have to, you'll have to only depend upon things like bending of light in its vicinity and so forth. But there has been some speculation, and which are all borne out, And then we know now we can easily find black holes with X-ray binary system. So what's the X-ray binary system? So what is the binary system of stars? So nearly all stars in the galaxy are binary systems. There could be 3 stars, 4 stars, but mostly they are binary systems where there are 2 stars which are going around each other. So and then there will be an orbit, and you can see that binaries happen studied to death. You can see study binaries because of the variation of light as they go across the orbit. Then one star can eclipse the other star, and therefore you get variation of light. And that is how you discover binaries. Other way of discovering binaries is to look at the spectrum, look at the wavelength of certain specific lines in the spectrum. Then you will find that sometimes the line periodically increases the wavelength, decreases the wavelength, increases the wavelength, decreases the wavelength. So why does that happen? That is because if one star is going around another star like this, then when you get light from the star, it will be Doppler boost. It will be a Doppler effect, and therefore the wavelength, a specific wavelength, will increase and decrease depending on whether the star is moving towards you or moving away from you. Now, what I have shown here, this is not actually the surface of the stars, but this is the gravitational fields around the star. So, if you are a single star, because the stars are very spherically symmetric, there are small deviations from that, a few percent, which we'll neglect for the moment. Spherically symmetric, and so the gravitational field will be spherically symmetric. But when there are 2 stars around each other, there are 2 different effects. One, if you take a piece of matter on one star, it is attracted to the center of that star, but it is also attracted to the center of the other star. So there are 2 forces acting. But there is a third force. When there are 2 stars in each other's vicinity, they simply cannot sit in their own place, right? Because then they'll just fall into each other. What you require is just like a planet goes around the star. Here in the binary system, one star goes around the other star in the binary system. Right? So that is how you get a binary star. And when you have that, then you see here, if you look at this, is not necessarily the surface of the star. Surface of the stars is inside, but the gravitational field. If I come to start from the center of one star, the force will mainly be due to the matter here. But as I move away, at one point, I will also start getting attracted. This force is also significant. This force can decrease. So then I'll eventually be captured by the other star. So if you look at the equipotential surfaces, and then if you take into account the fact that there are 2 forces acting, there are 3 forces acting on any one point here. One is the attraction of one star, the attraction of the other star, and then the centrifugal force because the 2 stars are in orbit around each other. Then you will get what are known as the Roche surfaces. So I got the Roche surfaces here. If I just take a cross section, let's take the orbital cross section, equatorial cross section, then I will see something like this. So when I go to close to one star, the equipotential is nearly spherical. Here also nearly spherical. But at one point here, I get what is known as a Lagrangian point. And at this point, at the Lagrangian point, if I sit at the Lagrangian point, then these 3 forces, the attractive forces of the 2 stars and the centrifugal force, they cancel each other. So if I park myself at this point, I'll forever remain at this point. But if I move slightly to this side, then I'll fall into this star. If I move slightly to this side, I'll fall into that star. Then there are actually 5 Lagrangian points. There's one here, L1. This point is called L1. There's L2, and then there's L3 here, and L4 and L5. So if you come to IUCAA, then you'll see that there are 2 trees here near the library, which have been treated as stars, and the Lagrangian points have been marked there, the 5 Lagrangian points. So you see that here you've got one star and the other star. And they're quietly sitting deep inside the Roche flow. Nothing is happening. It's just a binary. But out of these 2, let's say one star is more massive. Let us suppose the blue one. Why the blue one more massive? Because the more massive a star, the greater is the surface temperature and the bluer it will be. Now, the greater the mass of the star, the faster it will evolve. Right? In fact, the evolution time goes as a high inverse power of the mass, something like m to the minus 3 or m to the minus 4. So, if this has got the mass of the sun, then it will take 10 to the 9 years to 10 to the 10 years to evolve. Whereas this star here, if it has got just say 10 times or 20 times the mass of the sun, then you can count the evolutionary time in billions of years. Okay, so this will evolve quickly, it will expand, and it will form a red giant. Then I told you that as stars evolve, they expand. Now you see that one part of the star is touching the Lagrangian. So here you see the three forces are all balanced, but please remember that there is a fourth force here, and which is the pressure inside the star which is pushing the matter, and it is like a syringe, like a plunger of a syringe, and the matter rushes out of the Lagrangian point and starts moving towards the other star. And it is not going to go straight into it because it has got angular momentum, and therefore it goes round and round and round, and it can form an accretion disk, but depending on the circumstances. Otherwise, the accretion disk can blow it up and so on, and you can have a common envelope binary. And so you see, this can blow up, and it just transfers mass to that, and then this star can eventually this star will blow up, and it's a very complex evolutionary history. But because of this evolutionary history, and if the conditions are right, what can happen is that you start with a binary system in which one star is much more massive than the other. The more massive star evolves faster, and eventually it explodes. But before it explodes, it transfers quite a lot of the mass to the other star. And then when it explodes, because it has started with a high mass, then it will have either a neutron star or it can have a black hole at the center. Right? So then what happens after the first phase of evolution is finished? So we started with two more or less normal stars, and the end product of the first cycle of evolution is that I got one star here. I got one star which is left and other compact object which is left. And then when the one is actually a star, when it itself evolves, it will fill the Roche, and then the stream of matter which goes to the compact object. And what is that compact object? It is either a neutron star, or it is an X-ray, or it is a black hole. It could also be a white dwarf. If when it is a white dwarf, then a system which consists of a normal star which is feeding matter to the white dwarf is known as a cataclysmic variable. But today we are interested in black holes. And so we leave cataclysmic variables apart, and then we talk about the normal, a binary consists of neutron stars and black holes because they have a common property. Okay, so you see here, this is a famous X-ray source called Cygnus X1. So where the star is pouring matter into it, you can see the accretion disk which is formed. This is all hypothetical, right? Meaning that it got a real astronomical image. And then, now what happens is that the accretion disk can get extremely hot and it emits X-rays. So the X-rays which are emitted can interact with the rest of the matter which is present here. And because of many different processes, which include black body emission, plus it includes scattering of the photons that can have Thomson scattering or it can have inverse Thomson scattering. And therefore, you have the whole electromagnetic spectrum which is generated there. And much of the energy is emitted in the form of X-rays. And this kind of an object, where there is one object in the star which is feeding matter to the other one, where either you've got a neutron star or you've got a black hole, is known as an X-ray binary system. Right? So now there are two kinds of X-ray binary systems. One where the mass of the star is greater than the mass of the compact object. And the other one is the mass of the star is less than the mass of the compact object. So when is it greater, then you will get what is known as a high mass X-ray binary. And high mass X-ray binary is unstable because the transfer of mass can become quickly unstable, and they've got a relatively small lifetime of 1 million years or so. Whereas If the mass of the star is lower than the mass of the compact object, then the outflow of matter can be very steady and the objects can exist for a very long time. And then they are known as low mass X-ray binaries. Right? So, so you've got the high mass X-ray binaries, and then you've got the high mass donor and low mass donor and intermediate mass donor. What we are interested in today is is not the distinction between high mass and low mass, but the distinction between whether it is a neutron star or whether it is a black hole. Now, I told you that a black hole has no structure. It has only got a mass and spin. Whereas a neutron star has got structure. A neutron star is a finite sized object. It has got it has got a surface. So, and the neutron star is spinning. And you know that a fast spinning neutron star, which has got a high magnetic field, is a pulsar. So just like you've got radio pulsars, you've got also X-ray pulsars. So if you look at an X-ray binary, how do you know whether the compact object is a is a is a black hole or it's a neutron star? There are two different ways in which you can do it. One way is that if you see any pulsation, okay, regular pulsation, then it is called X-ray pulsar. Pulsations require a neutron star because a black hole has no structure. A black hole is spinning, but there is complete axial symmetry there. Whereas a neutron star, when it spins, can have asymmetries, as a result of which the pulses get emitted. There's also another thing. When matter falls onto a black hole, after it passes through the ISSAA, then it just falls into the black hole, goes through the event horizon and onto the singularity, and you'll never see any of it again. Whereas a neutron star, as the matter goes closer and closer to the neutron star surface, eventually it actually hits the surface. And when it hits the surface, it suddenly gets heated. Just like a ball thrown onto the Earth's surface and it bangs into the Earth, you'll get heated. Right? So the matter gets heated and then you get what are known as X-ray bursts. And so if you find X-ray bursts coming from the binary system, then you know that it is a neutron star and not a black hole. But there is another plan. You must have heard of the Chandrasekhar limit on a white dwarf mass. So I'm going to be lecturing to you about that later in the course. So, so there the mass limit for a white dwarf is 1.4 solar masses. If an object has got more mass than that compact object, then it cannot form a white dwarf. Similarly, then it forms a neutron star. But there's also a mass limit for neutron star, which is not known exactly because there are a lot of unknowns to it. And it turns out that neutron stars have a maximum mass of about 3 solar masses. So if you actually work on the binary system and get enough data by looking at its variability and so forth, then you can evaluate the mass of the compact object in the most favorable circumstances. Not always, but in the most favorable circumstances. And if you can argue that the observed mass is significantly more than 3 solar masses, because there are large error bars, then you know that it cannot be a neutron star, it cannot be a white dwarf, and the only other compact object that we know is a black hole. There could be things like strange stars, etc., which people work on. Those possibilities are indeed there. You can have a stage between a neutron star or a black hole, but such objects have never been found in observations. Right, so look at an X-ray binary, and then you say, by God, the mass here is 5 solar masses, 8 solar masses, 12 solar masses. So it clearly can't be a neutron star. It has to be a black hole. It takes a lot of argument and persuasion to do that. And it has been, so I think that there are about 20, 30 sources for which black hole masses have been determined with confidence. Where you can say with confidence that the compact object is a black hole. So that is how you discover stellar mass black holes. Now I'll end my talk in the next 5 minutes by actually coming to a very interesting, very recent development, and which is the detection of gravitational waves from inspiring binaries. As all of you know, there's a LIGO detector. LIGO stands for Laser Interferometric Gravitational Wave Observatory. There are 2 LIGO detectors for detecting gravitational waves. One is in Hanford in the US, the other is in Livingston in the US. There's a similar but smaller, less sensitive detector called Virgo in Italy. And there is another detector called Kagra, which is in Japan. Now, if all goes well, we'll also have a LIGO detector in India in the next 5 years or so. So therefore, you see that the LIGO detectors have been around for 30 years, but it was only in 2015 that they completed an advanced version of the LIGO detectors. Okay, and they thought that they got enough sensitivity to detect neutron star by the leaves. Finally, after 20 years of trying, there was on the 14th of September, this is in the American notation, so 14th of September 2015, a gravitational wave was detected. And the shape of the wave, you can see it from the gray colored one is the shape of the wave which came in. And this is not what you actually observe. This is the reconstruction from the observation. And so you see that it is going up and down, up and down. There is this very beautiful waveform. And as you go closer, you find that the distance between the maxima is decreasing. And then you come at some point, it goes up to maximum amplitude, and then it just goes down and it's that. So what is this due to? It has been shown conclusively that this corresponds to two black holes which are in orbit around each other. So this is not a black hole and a star. It's just two black holes which are in orbit around each other. And then when they go, it's a very tight orbit. As they emit gravitational waves, they lose energy. And as they lose energy, they move closer to each other. And when they move closer to each other, they go faster and faster and faster. And moreover, they also emit energy at a higher and higher rate. So this is like a cascading process. Okay, meaning that you see that this is the frequency of not the going around, which is also the frequency of the gravitational wave. And then as they go around faster and faster, you see the frequency is increasing. And here they are they come to the highest frequency. The black holes are moved close to each other, and here they are merged, and then they have formed a single black hole. And what is this here? So after you have formed a single black hole, the black hole has complex properties. But I told you that a steady state black hole can only have a mass and spin and nothing else. Right? So this black hole, which has all kinds of non-uniformity in space memory, so that settles down by going on emitting gravitational waves, it just settles down to a steady state. And so this is known as a ring down. And why is it known as a ring down? That is because when you ring a bell and you go on striking it, it goes on ringing and you stop ringing, and then you see that gradually it cools down. Okay, so the sound becomes less and less loud, and it goes to lower and lower frequencies, and eventually it stops. So this is like a ring down. This was first talked about by Professor C.V. Vishweshwar in 1970. So here you see that as the black holes are moving close to each other, so the velocity of the black hole is just increasing, and it is as high as 0.6 the velocity of light when they merge. And the separation here you see is decreasing. And then there's enough data in the wave to make very detailed measurements. And the mass which is here for the black hole, you can say that the two black holes, before they merged together, had a mass of 36 and 29 solar masses. After the merger, they had a mass of some 62 solar masses. So where did this 36 plus 29 is 65? So where did the other three solar masses go? So they went into actually the emission of gravitational waves. So within a fraction of a second, 3 solar mass worth of mass was converted. 3 times the mass of the sun was converted into gravitational waves. And what about the spin? You can say that the spin of the black hole, A by M, is 0.67. You can also measure the distance and so forth. So this is one of the great measurements of our time. And it happened, yes, when it was announced, we were all sitting in the Homi Baba auditorium and listening for it. And so you see here, uh, the 3 into 10 to the 30, 56 ergs per second with a peak gravitational luminosity. And what is the luminosity of our galaxy? So there are, supposing all stars in our galaxy are like the sun, they would each emit 10 to the 33 ergs per second. There are 11 stars. So how many stars are there? 10 to the 33 into 10 raised to, not 11, 10 raised to 11 stars. So that becomes 10 raised to 44. How many galaxies are there in the observable universe? About 10 to the 10. So that becomes 10 to the 54. So you see that the amount of energy which was emitted at the last stages of the collapse was 100 times more than the stars emitted continuously by all the stars in the universe being emitted continuously. So it outshone the whole universe for a split second, except that the universe is emitting at optical wavelengths, X-ray wavelengths, and so on, whereas the binary emitted specifically at gravitational wavelengths. So if you did have a gravitational wave detector, then this would have gone completely unnoticed. And how do we know that these objects are black holes? You see, the point is that the highest frequency indicates that these objects, highest frequency of rotation, indicate that these objects must have moved closer to each other within 200 kilometers. Now, imagine a star like the sun, two stars like the sun. Can they move within 200 kilometers of each other? They can't. Because the sun has a radius of 700,000 kilometers. So if it comes to another star like itself, the stars will just wreck each other. And so therefore, in order for the two objects to move so close to each other, that they need to be very compact. But remember that, so therefore they are very compact objects. They can't be white dwarfs. Can they be neutron stars? They can't be neutron stars. And that is because the mass of one object, as I told you, is something like 36 solar masses. The mass of the other object is 29 solar masses. So they must be black holes. But I should tell you that in about a year's time after they discovered this source, black hole binary, there are many recent black hole binary which are known. They also discovered a binary neutron star. And the last thing I want to show you today is this amazing diagram based on LIGO. Yeah, based on LIGO observations. And what it does is that, so you see, here is the, this one on this axis is the, sorry, one moment. Okay, so so these are the masses of the compact objects which are discovered so far. And you see that these are all the electromagnetic neutron stars. What do you mean by that? These are the neutron stars whose masses have been measured, okay, whose masses have been measured uh, due to there being in X-ray binaries or there being in X-ray binaries or there being pulsars and so forth, binary pulsars and so forth. And these are the electromagnetic black holes, meaning that these are black holes which are in X-ray binaries, and you detect them through the electromagnetic radiation, not from the black hole, but the X-ray binaries. And the others are all, these are all black holes which are being discovered by LIGO. And so you see that I explained to you how these low mass black holes are formed, with mass below about 20 solar masses in the evolution of stars. But these black holes also are formed in the evolution of stars. But they cannot be formed in a normal evolution of normal stars because the mass is simply too high. And if I get the time, then I will tell you about, I just mentioned very briefly about how such black holes can be formed. Okay, I'm done for today. Thank you very much. And I should say here that tomorrow my lecture will be at 11:30 in the morning. It was originally scheduled for 2:30, but it has been changed to 11:30 because I asked for the change by something else to be achieved. Thank you. Any questions?
Yes, sir. Good afternoon.
Yeah.
Yes, sir. My question is that during the observation of the merging of two black holes, so how much time it takes from the merging to the settling down to a larger mass black hole?
The whole process, the entire observation lasted for about 0.7 seconds. So you can just imagine how fast it is. I mean, you have got these amazingly massive black holes and they're coming close to each other. They're finishing the spiral, they're smashing into each other, they're settling down, and they're emitting so much energy. All that happened in about 0.7 seconds. But the lower the mass of these objects, the longer it will take. So neutron star binary will take a few seconds to settle.
Sir, my another question is that a black hole form a black hole when it forms, it has a definite mass, but when it forms in the black hole, it engulfs various mass like stars, neutron star like that. So
Yeah.
how does it engulf so large amount of mass? How it contained?
There's no problem. The mass is just completely torn apart because of the tidal forces. As the star comes closer and closer to the black hole, it will get torn apart completely, and then it just forms a stream of matter which goes into the black hole. Sometimes, if it approaches very close, it can just swallow the whole star. Tarak, finished. So there is no problem. I mean, and as it swallows the matter, it goes on increasing in mass. So it can do that. I mean, it can go up to 1 billion solar mass. There's no problem. As I told you, black holes are scale free.
And so there is no limiting.
Let us go to somebody else. Let us go to somebody else now. Does anyone else have questions? Yeah. Sachin Dubey.
Yes, sir. Good afternoon, sir.
Yeah.
Sir, my question is like when you said these black holes, we get the gravitational waves, right, from the remaining mass. So, and we know that these black holes does not allow anything to go from their region, right, region of influence. So, how does these gravitational waves escape from its region?
No, you see that you have got the thing escaping from inside. Nothing escapes from the event horizon. The gravitational waves are being emitted continuously when the things are black hole. So what happens is that as they move closer and closer and closer, so that gravitational waves are not really emitted in the sense that an electromagnetic wave is emitted. Gravitational waves, because a black hole produces space-time structure, and that space-time structure which is variable. But what is most important is that as you form either a short-shell black hole or a curved black hole with mass and spin, once the black hole is formed, then there is no emission of any kind. Okay, so it is everything is happening during the formation of the black hole.
Okay, so sir, is that we know that black holes actually engulf everything, like swallow. So while merging the black hole, why two black holes merge rather, which is having a dense mass, does not swallow the another black hole, is actually merges? Why it happens?
Okay. I mean, look, I mean, it's all just a question of words, right? So just look at the physical process. Don't go by the words. Swallow, merge, these are all the same thing. What happened before is that is that there were two black holes to begin with, and now there's just one black hole. So when you put a piece of chocolate in your mouth, you're just swallowing the chocolate, right? Because the chocolate is small and you're much larger than that. Okay, but in other cases, when the two bodies are comparable, you can just call it a merger. The physical process is that you started with two objects and you got one object. Okay, then who else? Vikash?
Am I audible, sir?
Yeah.
Could you go to the slide where you explained the Penrose process?
No, I did not actually explain the Penrose process.
Not the Penrose process, but the graph that you showed.
Which graph was it?
about the amount of energy extraction, the percentage of energy extraction. 40th.
Yeah. Yes, yes.
So, from this, I can understand it is possible to extract energy from a rotating black hole. But how is it possible from a small shell black hole, actually?
No. You see, you're not extracting energy from the black hole here. Not that part. It is just that matter is falling into the black hole. Right? So you see, let us suppose that there is a particle which is going round and round in the black hole. Right? It will typically be the potential well. So if you look at all the dynamics, its energy of that particle is constant. But if I extract energy from the particle, let me go to that one and explain this is an important point. And Schwarzschild black hole. So just look at this one. Okay. So supposing I got a particle which is going down here, and please remember that the energy is a constant. So it will go on indefinitely in this elliptical orbit. But supposing by some means I extract energy from that particle, then it will have less energy. If I don't extract angular momentum, then the potential well remains the same. So this particle will come down here. And eventually, as I go on extracting more and more energy, it just will come to the bottom. Right? But what do I mean by it? How will I extract the energy? I could extract it, for example, by a single particle, then there could be tidal energies to other, it become complicated. But if it is a stream of particles there, then the stream of particles can have friction. One stream, one ring of particles can exert friction or viscosity on the other ring, and therefore extract energy, and it goes down. But typically, during this energy extraction, you are also extracting angular momentum. Right? So therefore, what happens is that when you extract angular momentum, then you see that you start with a high angular momentum here, and then you extract, so the particle will be here. As you extract energy for the particle, you also extract the angular momentum. So then you get a different well, and the particle will be deeper in the well. And it goes on like that until the angular momentum comes to this particular critical value at which R min is equal to R max. So after this, you can't extract any more energy because the particle will not be in a stable orbit. It quickly falls into the black hole. And so that's what the maximum energy that you can extract by whatever process you have in mind is to go from the energy 0 at infinity to this particular energy, and that is E. So that is that 1 minus E. So the petrol process is not that. Petrol process is crazy because here, you see, you have got the ergosphere, and because everything is spinning in the ergosphere, so therefore it is as if the mass of the black hole consists of its own mass corresponding to 0 spin plus energy corresponding to the spin of the black hole, which is also a mass. And it is that mass which you can extract. So for a mass hole, if you start with a black hole of a given mass and given spin, then there is something called an irreducible mass. And you can only go up to the irreducible mass, but not beyond that. Okay, then is there a last question? Or I'll stop because it's getting very late now. You have to go to the next lecture. There's one hand I see here. Who's that? No, there are many hands actually. 84F4FA31. No, that's not it. Okay, Sachin Venkatesh, last question.
Yes, sir. Thank you. Sir, actually, I wanted to ask about like when a black hole has an ergosphere where things can still escape, and within the horizon things cannot escape. They eventually fall into the black hole. So when two black holes are trying to coalesce, then according to the no-hair theorem, there shouldn't be any information loss. So when two black holes coalesce and produce gravitational waves, there is something that is generated due to that collision and their merger. So doesn't that itself solve the information paradox?
No, you see, I don't know those matters in detail actually. So I wouldn't like to answer this question. But there have been endlessly asked questions and endlessly given answers for all these things, but I'm not familiar with them. Because there's a question of entropy, there's a question of information, and the question of how to relate the two things, the question of temperature. So I would not really. When you're actually given lectures on black holes in this series, you please ask the question of them. Okay. All right then. Thank you very much. So see you tomorrow at 11:30. Those of you who will be here.